As seen in Table 1, the first of the sub-dimensions consists of 5 items, items 1 to 5, and the second consists of 5 items, items 6 to 10. Hello everyone, in this video, we will explain how validity analysis can be done with SPSS. But first of all, I must state this. If you lack information about what is validity, what are the methods of determining validity? What is the difference between validity and reliability? I suggest you watch the relevant videos on our channel first. After this suggestion, we can move on to our video. As we have just mentioned, in this video we will explain how validity analysis can be done with SPSS. However, what we will actually do here is to determine the construct validity, which is one of the different types of validity. Because validity is divided into subheadings such as face validity, content validity, construct validity, internal validity, and criterion-related validity. Therefore, when determining whether a measurement tool is valid or not, all of them should be considered if possible. What we will do here is to determine the construct validity among them. Therefore, we will use factor analysis. Because factor analysis is used to determine construct validity, let's briefly explain what construct validity is. Construct validity, in its simplest definition, means that the questions or items of a test or questionnaire are compatible with each other, complete each other, and collectively form a whole. Here, we will try to determine this with our analysis. For this, we will use factor analysis, which is one of the two types of factor analysis, called exploratory factor analysis and briefly expressed as EFA. This analysis is used when the researcher has no information about the factor structure of the items. There is also confirmatory factor analysis. Confirmatory factor analysis, on the other hand, is used when the researcher has prior knowledge of the factor structure of the items and wants to confirm it. In other words, there are two factor analyses, exploratory and confirmatory. What we will do here is exploratory factor analysis, which is briefly expressed as EFA. I explained them because I thought it was important to know what we were doing. After briefly talking about the difference between exploratory and confirmatory factor analyses, let's now move on to how the construct validity of a measurement tool is determined by doing EFA. That is, how this test is done. We do this by following the path we have seen on the screen. We come to the factor analysis from the dimension reduction section under the analysis menu. When we click on the factor analysis here, this window that we see on the screen opens. Here, we would like to include 10 items here in factor analysis. We want to determine what kind of factor structure these are, what kind of sub-dimension structure they have, and whether the items are compatible with each other. What do we need to do for this? Here we select the items. After selecting all of them, we transfer them to this part. After doing this, what we need to do is to mark some options from the menus here. After that, we will run direct factor analysis. Let's start with the first menu. Let's start with descriptive statistics. For this, we tick the option here. When you mark this, we will be able to see some information such as the arithmetic mean and standard deviation of the items in a table in the factor analysis report. After that, we mark all the options you see from the options here, as I did. There is no need for the inverse option here, but we tick all the other options. After doing these, we press the Continue button to continue. We come to our second menu. When we click on our menu here, we see that the principal component method is selected by default. We are not changing this, because this is the method often used. Then we tick the scree plot option here. Then we don't make any changes here. Click the Continue button. Then we see a menu called Rotation here. This means rotating data. We open this. Why is there a menu here that means rotate? Because in the factor analysis we have done, there is an analysis created by statistically rotating the data. A result is obtained by rotating the data. This is how factor analysis is performed. So here we need to choose a rotation method. But first of all, we should know that among the methods here, if we draw a line, the top 3 are in one group, and the bottom 2 are in a different group. What are these groups? Here, the 3 methods above are in a group called orthogonal rotation. The 2 methods here are in a group called oblique rotation. In other words, the 3 methods above do orthogonal rotation. The 2 methods below do oblique rotation. We have to choose between them. So how do we choose between these 2 groups? We do this according to this. If we think that the factors that will emerge as a result of the 10 items here are not related to each other, then we need to choose one of the orthogonal rotation methods above. If we think that the factors that will emerge as a result of the items here are related to each other, then we need to choose one of the oblique rotation methods here. In researches in the field of social sciences, there is usually a relationship between sub-dimensions, that is, factors. That is, they reach a conclusion in a relationship. For example, our scale here is the job satisfaction scale. The items here are items to measure job satisfaction. We think that sub-dimensions such as internal satisfaction and external satisfaction that will emerge from the items here are related. Therefore, here we need to choose one of the oblique rotation methods based on the interrelatedness of the factors. So, which of the methods do we choose here, after determining the group? Here's what we need to know for this. Let's talk about the top group first. The most frequently used method in the upper group is the Varimix method. The Varimix method is used when the number of factors is desired to be as large as possible. The Kortemax method is used when it is desired to keep the number of factors low. So, the number of factors is too high here. Here, the number of factors is less. Generally, the Varimix method is used if one of the orthogonal rotation methods is to be preferred. If one of the oblique rotation methods is to be preferred, then the direct Ablimin method is selected. The difference between direct Ablimin and Promax here is that Promax is used in data sets consisting of thousands of data. When there is no such situation, that is, the number of data is not thousands, the direct Ablimin method is used. We will use the direct Ablimin method here. Because I already said it. We think that there will be a relationship between the factors that will emerge. Therefore, we choose the direct Ablimin method, which is one of the oblique rotation methods. Then we tick the loading plots option here. We want a graph in the report that will appear. We will tell you what it is. After completing our selections here, we now press the Continue button. Our next menu here is Scores. We are not doing anything about it. We go to the next menu, namely Options. Here, what we need to do is tick the option here. What does it mean? After making the marking here, let's write it as 0.30. After doing this, let's explain. We will soon have a table showing the factor loadings in the report. In this table, each item will have factor loadings. We do not want to show the loads in that table if the factor loads are less than 0.30. Because factor loads below 0.30 are not very important to us and we do not want them to cause confusion in the table. Therefore, we marked this option and wrote 0.30 here. If we want, we can also tick the Sorted by Size option here. When we mark this, the items listed here from 1 to 10 will not be listed in this way, in the report, in the table there. This time the factor loads will be listed from the largest to the smallest. I don't want this order. I want to see this order. So, I want the items to be sorted from one to the next. That's why I'm not marking it here. After completing our selections here in this way, we can press the Continue button. Thus, we have done all of our selection processes here. Then we can click OK. When we click OK, our report will be created. In our report, we first see the descriptive statistics table. Since we just wanted to see this, here we can see the arithmetic mean and standard deviation of each item, as well as the number of participants included in this analysis, in this table. After that, we also see some tables and graphs. We will evaluate factor analysis by looking at these. However, we will divide the readings we will make here into two groups. First of all, I want to divide them into two groups. In the second step, we will read the factor analysis results. Before that, in the first step, before we move on to the factor analysis results, we will examine how suitable our data are for factor analysis. For this, we will make 4 different analyses before the factor analysis results. Our first review will be the chart here. What are we going to examine in the table here? Here, we will examine the correlation coefficients between the items themselves. Here we see a table called the correlation matrix table. First of all, there is the correlation table. So, there are correlation coefficients. Here are the significance values. First of all, when we examine the correlation values, we can see the correlations of each item. For example, the first item with the second item and the third item with the fourth item. We can see the correlation coefficients. If we recall what the correlation coefficient was, it was a coefficient that took values between -1 and +1, and the correlation increased when it approached -1 or +1. Here, we want relations between our items at a medium level, that is, not too high, not too low, and we want these relationships to be meaningful. At the same time, if the items of our scale are items in the same direction, for example, if all items are positive, we want all of the correlation coefficients here to be positive. First of all, when we want to evaluate the correlation coefficients, we can define a criterion like this. We can examine whether there is 1 less than 0.10 or 1 greater than 0.90. When we examine it here, we see that there are generally the correlation coefficients we want. So, are these results, these relationships, meaningful? We also check this part here. Relationships are significant if the coefficients here are less than 0.05. If it is greater than 0.05, the relationships are meaningless. We see that the coefficients here are generally lower than 0.05. I just see a meaningless relationship here between item 10 and item 5. The reason for this can be investigated by returning to the scale items and making an examination. Also, I see that there is a non-significant relationship between the 10th item and the 4th item. These can be examined. However, in general, we can say that the results are good. But what does it mean when it is significant and the relationships here are moderate? This means that the items here are self-consistent. There is harmony between the materials. Therefore, it gives us a good result regarding construct validity. In short, we can express it this way. In addition, we need to pay attention to one more result in this table. That's the explanation that says, determinant, that we see here. We want the value specified in the description here to be greater than 0.00001. When this happens, that is, if the value here is greater than 0.00001, we can understand that there is no problem called multicollinearity between the items here. Let's briefly describe what multi-connectedness means. Multicollinearity means that the correlation between the items here is very strong. When the correlation between the items here is very strong, that is, when the multicollinearity problem arises, the strengths of the items cannot be clearly understood. Items will not be able to show themselves sufficiently in factor analysis. Therefore, we want there to be no multicollinearity problem here. We understand this by looking at the value here. We want the value here to be greater than 0.00001. In our study, we see that this condition is met. Therefore, all of the data in this table showed us that these items were suitable for factor analysis. Now we can move on to the next table. I mentioned that we will go through 4 stages before we move on to the factor analysis results. Now we have come to the second stage. In the second stage, we need to read the table that says KMO in Bartlett's test. KMO here stands for Kaiser-Meyer-Olkin. Here is the abbreviation for it. The KMO value is a value that indicates whether the sample is sufficient. In other words, there is a value here that answers the question of whether the amount of data in our sample is sufficient to perform factor analysis. We want this value to be greater than 0.50. In some sources, it is desired to be greater than 0.60, but it is sufficient to be greater than 0.50. We will add the source for this in the description of the video. This value is greater than 0.50 here. Therefore, we can say that the sample is sufficient. In addition, a value between 0.50 and 0.70 means that the sample is moderately sufficient. Between 0.70 and 0.80 is considered good. Between 0.80 and 0.90 is considered excellent. 0.90 or more than that is considered perfect. Here our value is 0.87. Therefore, we can say that the sample is excellently adequate for factor analysis. After reading these, here is a test result called Bartlett's sphericity test result. We also need to look at this result. Here, we want the significance value here to be significant, that is, to be less than 0.05. Such a result means that the correlation between the data is sufficient for factor analysis. In summary, we want the KMO value here to be greater than 0.50 and the Bartlett's value here to be less than 0.05. Also, here is another table. This table is also linked to the table here. If the value here is below 0.50, we can determine which items among the items here negate the value here by looking here. Here we examine the bottom part of this table. In the lower part, we look at the place where each item coincides with itself. So here we are looking at cells with the letter A on them. The cells here show the KMO value of the first item here. The value here represents the KMO value of the second item. The value here shows the KMO value of the third item. This way it goes from left to right and down. If the value here does not turn out as we want, there will be a value below 0.50 or there will be more than one value. Thus, we can determine which substance causes the negative result here. After doing this, we have now completed the second stage. We said that we will go through 4 stages before we move on to the main findings of the factor analysis. We have completed the second phase. In the third stage, we examine the table called communalities and showing the common variance. This table shows us the variance explained by each item in scale. We see it here. Or it shows the common contribution of each substance. We want the values here to be greater than 0.66. Or if there are more than 250 participants, we want their arithmetic mean to be at least 0.60. However, this may not be easy to achieve. Different sources mention different values. Usually, it is desirable that these be close to 1. It is undesirable to be below 0.50. Thus, an evaluation is made on how much these items contribute to the common variance. When we examine the values here, we see that the lowest value is 0.60. Therefore, we can say that they are good values and we can say that your data here is sufficient and suitable for factor analysis. After that, here we see the total variance explained, that is, the table showing the variance explained by the factors as a total. This is the main table that we will evaluate as a result of our factor analysis, but we skip that for now. By the time we read this, we had completed 3 phases. Here was the third stage. Our fourth step will be the examination of this remaining table. We see 2 sections in this table. I would like to briefly explain this. The correlation coefficients here show the relationships between the items. However, these are not the actual correlation coefficients between the items. We have previously examined their true correlation coefficients in the above table. Here, there are correlation coefficients calculated by SPSS according to a model created in factor analysis. So, these are the correlation coefficients of the model. Between items, Here are the values that show the difference between our true correlation coefficients, expressed as residuals, and the correlation coefficients of the model here. So here we see the difference between the values here and the real values. So, what do we want to achieve from here? We do not want the difference between the correlation coefficients of the model here and the real correlation coefficients to be more than 0.05, but it is really difficult to achieve this. Many values will be higher than 0.05. For example, we see it here. It was found to be 0.08. For example, we see it here again, 0.07. Here we see it again, 0.08. Many places have values exceeding 0.05. Therefore, we say that it is sufficient for us that more than 50% of the values here do not exceed 0.50. So how do we determine if more than 50% of the values here exceed 0.05? Do we need to count this? No, we don't have to count. Here we see an explanation. There is an explanation in this statement that 37% of the values here are greater than 0.05. It says greater than 0.05. 17 values are greater than 0.05 here. So, 37%. We consider it sufficient that more than 50% of the values here are not large. Therefore, 37% here is within acceptable limits for us. Thus, we have met our 4 conditions before the main report of the factor analysis. After that, we can move on to examine the table showing the actual results as a result of factor analysis. Let's take a look at this table. So, what does this chart tell us? The title of this table is Total Variance Explained. So how much of the total variance does our measuring tool explain? How valid is it? The value we will determine here will indicate the validity of our measurement tool. He'll give us a percentage. So how do we read this table? In this table, first of all, those who write components here are the factors. It goes from 1, 2, 3, 4, 5 to 10 here, as you can see. However, here are our values to determine how many factors there are. There are as many factors, that is, sub-dimensions, in our measurement tool, as many rows as there are among the values here. If we pay attention here, we see that there are 2 sub-dimensions, 2 factors, because we see 2 values above 1. These values are called eigenvalues. In addition, the variance explained by these factors appears here. We see that it is 71.307%. In other words, the total variance explained by these 2 factors is 71.307%. Here we see the first of 2 factors. It explains 47.938% of the variance. In other words, the contribution of the first factor is 47.938%. The contribution of the second factor and the variance explained by the second factor is 23.369%. When these are added together, 71.307% is reached. If the value here is more than 50%, it means that our measurement tool can achieve the purpose it wants to measure. In general, more than 50% of the sources are considered sufficient. Therefore, we can say that 10 items in our measurement tool show a valid feature. In addition, 71% here draws our attention as a good rate. We can say that the validity of our 10 items is at a good level. Well, here we see a chart called scree plot. What does this chart tell us? This is a slope chart. This is called a slope chart. Here is what we pay attention to. There is a decrease after the first item. There is also a decrease after the second item. Then we see that there are 2 sub-dimensions here. Starting from the third item, a flattening started. In this way, from where the flattening starts, we do not count them as factors, including the factor here. We understand that there are 2 factors here by looking at this graph. Thus, we have determined how many factors there are, how many sub-dimensions we have, the variance explained by each factor, and the validity level of the scale in total. We have confirmed this from the graph here. After that, we move on to a very important table. At least as important as the previous chart. That's the pattern matrix table we've seen here. The table here shows us which sub-dimension each item falls under and also the factor loadings. That's why this table is so important. How do we read this table? First of all, this table will contain as many columns as how many subdimensions we have just found. There are 2 columns here because we just found 2 subdimensions. These are named 1 and 2. Here are our items. Here we see some values. The values here are the factor loads, as we have just mentioned. Let's briefly explain what factor load means as follows. We can express the factor loads here as values that show the relationship of the items here with each factor or their contribution to each factor. The factor loads here take a value between -1 and +1, and we want the values here to be close to 1, regardless of minus or plus. We also want the values here to be greater than 0.40. The substances here will be able to make a sufficient contribution when it is greater than 0.40. We also want the loads here to be in only one subdimension. We want the value here to be above 0.40, for example, and we don't want it to be written here. Here we see an example of this. Here we have 0.331. Here we have 0.606. We don't normally want items like this, because we want an item to be in only one subdimension, that is, the factor. When this happens, we want a difference of more than 0.10 between them. We don't want the difference to be smaller than 0.10. When this is the case, that is, when the difference is less than 0.10, such items, the 6th item here, for example, are called overlapping items. We don't want any overlap. We do not want an item that falls under 2 factors. When we examine the values here, we see that there is a greater difference between 0.331 and 0.606 than 0.10, so it's acceptable. Since the larger value is here, we include the item here in the second subdimension, the second factor. Therefore, we can say that the first, second, third, fourth and fifth items of the scale here are in the first subdimension, while the 6th, 7th, 8th, 9th and 10th items are in the second subdimension. In addition, we can more easily understand what this table means through the graph here. If we pay attention, there was a case of taking place in both subdimensions even though the 6th item was not overlapping. That is, the difference was not very small. If we pay attention, we see that the 6th item is located at a point between the group here and the group here. The line here is the line of the first factor. The line here is the line of the second factor. We can see the values on the first factor here. There are values ranging from -1 to +1. These are the values of the line here. The items here got values very close to 1 on the first factor. Here, the table we can see them on it. There are values very close to 1. But the value of the 6th item is 0.518 compared to the first factor. If we examine it here, we see that the 6th item is located at a point that corresponds to 0.518. The items here are clustered in the second subdimension. Here again, these values are close to 1. So they are clustered here in this way. Therefore, we see that the items here form a separate subdimension, while the items here form a separate subdimension. Therefore, we want the factor loads here to be as close to 1 as possible and to be separated from the other factor. In this way, when both subdimensions are loaded, the item here is somewhere in the middle. We do not want such a situation. Here, item 6 was placed between 2 factors. However, we included it in the second factor, as its value is greater here. Since the difference is greater than 0.10, there is no problem in including it in the second factor. After that, after examining the table here, we can also provide our controls from the structural matrix table here. Is the same subdimension structure formed here again? We can check it here. Here, we said that items 1, 2, 3, 4, 5 are in the first subdimension. If we pay attention here, we see that there is more factor load here. He's already here alone. Again, we see that it is greater here than the value here. Here again there are standalone values. The factor load of the 6th item is higher in the second subdimension compared to the table here. Therefore, we see that the same structure is confirmed here as well. As a result, we confirmed which factors the items were included in. Now we can move on to writing them. Let's show how we can report factor analysis results. Exploratory factor analysis, EFA, was conducted to determine the construct validity of the Job Satisfaction Scale, JSS, and to reveal the factor structure. For this, principal components and direct Ablimin rotation methods were used. The reason for this is that the principal components method is the most frequently and easily used method in practice, and the direct oblique rotation method is used when it is considered that there is a relationship between the factors. Initially, the Kaiser-Meyer-Olkin (KMO) sample adequacy value was found to be 0.873, showing that the sample size was sufficient for EFA. This value is considered sufficient when it is above 0.50 by Field, 2009. And classified in the excellent category between 0.80 to 0.90. The KMO values calculated for each item were also found to be the lowest 0.820, confirming that the sample was sufficient. In addition, as a result of the Bartlett's test X2, 45, equals 1578.084, p less than 0.05, and this finding showed that the correlations between the items were large enough for EFA. As a result of the EFA, it was determined that the JSS, which consisted of 10 items, consisted of a structure with two sub-dimensions, factors, and these two factors explained 71.31% of the total variance. According to this, it was concluded that the JSS has a valid feature. In addition, the first of the sub-dimensions explains 47.94% of the variance, and the second explains 23.37%. Table 1 shows the distribution of the items according to the factors and their factor loads. As seen in Table 1, the first of the sub-dimensions consists of 5 items, items 1 to 5. And the second consists of 5 items, items 6 to 10. Factor loads were determined as the lowest 0.606. Therefore, as factor loads of 0.40 and above are accepted as ideal, Field, 2009 to 666. It was evaluated that the items contributed significantly to the factors. In addition, the factors were named as intrinsic satisfaction and extrinsic satisfaction, respectively.